All right. So the plan for today is to discuss one particular example of second order differential equations with constant coefficients. And this is an example you have probably seen before, so we will be a little brief about it, the case of damped oscillations. And after that, we will move on to certain general discussions about linear independence and uniqueness of solutions and so on and so forth. Just like we did for the first order differential equations. Okay. All right. So this is an example that we will be doing. Mass spring system. Okay. So there are many nice examples where in both physics and engineering problems where you directly employ these second order differential equations with constant coefficients. And this is one such example. So I hardly need to draw the picture, but I will draw it anyway for completeness sake. So you have a spring with some stiffness constant K, and you have a ball of mass M, okay? And this is a problem that you have done 1,000 times. And then you pull it downwards and displace it a little bit from its mean position, okay? So let's call this Y, and I'll call everything following a textbook, I'll call everything that is measured in the downward direction as positive. So gravity for me is positive and upward direction be negative. This is just so that I don't have to put in a bunch of negative signs. There is no physics or mathematics here. Okay. And then I displace it and then look at small oscillations and write down the equation that governs these small oscillations, which, as you know, is a simple harmonic equation. So there is a restoring force. The restoring force by Hooke's law is minus K times Y, where K is the stiffness constant. Okay. So this force always seeks to get back the system to the original position, right? So if this ball is going downwards, the restoring force is pulling it up, and vice versa. Okay, so what is the equation? Newton's law states that force is ma. So m d square y over dt square equals the force, which in this case is ky, and writing this as y double prime plus k over m y equals 0 yields us the famous simple harmonic equation. So I'll call omega 0 square as k over m, the natural frequency of oscillation. And this becomes y double dash plus omega 0 square y equals 0, which, as you know, has the solutions, excuse me, y of t equals a sine omega 0 t plus b cosine omega 0 t. And as you guys worked out in the tutorial, a and b can be fixed by appealing to initial conditions if this is an initial value problem. So this is the most general solution of the problem. And sine omega t and cos omega t are, of course, linearly independent solutions. And the general solution by superposition principle is a linear combination of the two. Okay. So far, so good. But of course, if you try to model this, if you take a spring and put in a mass and oscillate it, it's not just going to keep oscillating forever. At some point, it's going to stop. It's going to stop because there is always some drag, some frictional force, some damping force. And this damping force, there is no a priori understanding of how exactly the damping force should be. For example, if you immerse the entire thing in a medium, you'd have to model it slightly differently. But usually for small velocities, the damping force is modeled as being proportional to the velocity. So there is a damping force, excuse me, also called frictional force. And FD is usually taken to be proportional to velocity. So this is some c times velocity. And of course, it should not aid motion, it should oppose motion because it's trying to stop the bob from oscillating. So you should put in a negative sign. Okay. So if damping is also taken into account, then the equation of motion of the mass m can be written as my double dash plus cy prime plus ky equals 0, right? Newton's law simply states that my double dash equals the net force acting on the bob The net force is, of course, the Hooke's restoring force plus the damping force, both of which are negative. So I take both of them to the other side and write this as a simple equation in y double prime, y prime, and y. And since m, c, and k are some constants, and c is also a constant, then this becomes a homogeneous linear second order differential equation, ordinary differential equation with constant coefficients. So I'll put this in the standard form by dividing through by m. Okay. And then you can do the same old thing that you have done. You try a solution of the form e to the lambda x. Okay. And then or if you prefer writing everything in the operator notation, you write everything in the operator notation and write as d plus lambda 1 times d plus lambda 2 acting on y equal to 0, even though that is not required in this particular course. Whatever you do, you can get the solutions. So if you plug in e to the lambda x, the characteristic equation of the system, of course, y dash should bring in one factor of lambda, y double dash will bring in two factors of lambda. So this becomes lambda square plus c over m lambda plus k over m equals 0. Okay, so this will be the characteristic equation, which you can then easily solve to get lambda equals plus minus square root minus over 2. Okay, so remember that C is the damping. So C causes the damping. So what's interesting in this problem is to understand the effect of damping. So what happens if C is very large, very small, whatever it is. So we want to understand how the motion would be if the damping starts taking precedence. So let's first clean this up to write it in a slightly different form. So I'll write this as minus C over 2m plus minus, I'll write this as 1 over 2m square root c square minus 4mk. All right. So I'll call this some alpha and this is some beta. And so your lambda is minus alpha minus beta. And lambda 2 is minus alpha plus beta. So far, so good. So you can always write down the general solution as a e to the minus alpha minus beta times t plus b e to the minus alpha plus beta times t. But we still have to worry about what happens in three cases, depending on what happens inside the square root. The first case, of course, is, as we have discussed, when everything is real and there is two distinct roots. The second case is, of course, when there is the square root becomes 0 and you have only one double root. The third case is when the square root becomes negative, so you have imaginary values and we have an oscillating solution. So let's investigate these three cases very briefly, since we have done this already. So case 1 is c square is greater than 4mk. In this case, this is the usual case. You have two distinct real roots. So what does c square greater than 4mk mean? C square, the damping coefficient is large compared to m times k, which means damping takes precedence. Damping is a huge factor in this particular case. Okay, so this case is therefore called overdamped. Case 2 is when c square is not so large, but it's not very small either. It is just about equal to 4mk. In this case, of course, the square root becomes 0 and we have double real roots. And since c square is not too small, this case is usually called critically damped. Okay, and the last case, as you might guess, is when c square is not too large. It is there, but it takes a while to turn on, probably. So the value of c square is less than 4mk. So in this case, it will be interesting to see how the motion proceeds. So in this case, there is two complex conjugate roots of this equation. And this is called underdamped. The reason for these terminologies is because of the absolute value of c square. So c square being the damping coefficient, if it is very large, it's overdamped. If it is equal to 4mk, it's critically damped. And if it is small, it is called underdamped. So what does the solution in case 1 look like? Case 1, overdamped. There is two distinct real roots. So the solution can be written as y of t equals a e to the minus lambda 1t plus b e to the minus lambda 2t using the superposition principle. So in this case, y of t equals lambda 1t and lambda 2t. Okay, there is no negative. So what is lambda 1? Lambda 1 would be minus alpha minus beta, and lambda 2 would be minus alpha plus beta. So this is minus alpha minus beta. So minus of alpha plus beta times t plus b e to the minus of alpha minus beta times t. Okay. So what does the solution represent? Alpha is positive, beta is positive, alpha plus beta is positive. Okay. So this is an exponentially decaying solution. Okay. Any questions? Does this make physical sense? Yes, it does make physical sense, because it simply means that once you pull the bob and start the oscillation, the damping is so strong that it doesn't really start oscillating at all. It quickly goes down to 0. So if you plot y as a function of time, okay, let's say that you started with 0 initial velocity, then it simply dies down. Okay. If you pull it down to give it a little bit of positive initial velocity, of course, it can start going up, but again will die down because the exponential is too strong. It will always start dominating. Okay. So this is not really an oscillating solution anymore because the damping is too strong. Case 2 is critical damping. In this case, this general solution, as you by now should know, is C1 plus C2 times T e to the minus lambda T. What is lambda in this case? In this case, remember, lambda 1 equals lambda 2 equals lambda, which is just equal to minus alpha. Okay. So y of t in this case is C1 plus C2 times T e to the minus alpha T. Alpha is a positive number, which means this is again an exponentially damped case. Okay, it's gonna, if you graph this, this is gonna look very similar to the previous graph. Now, of course, when t is very, very small, exponential can be regarded as almost equal to 1. So at very, very small t, there could be a slight linear growth because of this plus c times t term. But for any appreciable t, the exponential is going to start dominating and pull everything down. And this is also going to go down very fast. So this is a critically damped case. And this case is interesting because it serves as an in-between of the first case and the third case. And the third case is quite interesting because in this case, you have two complex conjugate roots, because in this case, this beta becomes an imaginary number. So I can write lambda as minus c over 2m plus minus. So inside the square root, since in this case c square is less than 4mk, I will write this as I times 4mk minus c square. So I'll write this as I times 1 over 2m square root of 4mk minus c square. Since c square is less than 4mk, this square root is guaranteed to be positive. So I will call this minus alpha plus minus I times some omega star. Okay. So what will be the solution in this case? The solution in this case is actually quite interesting because y of t would be equal to, so there is an a e to the minus alpha. Let's call this, instead of omega star, I'll call this omega tilde. So I omega tilde times t plus b e to the minus alpha minus I omega tilde t. And there is an e to the minus alpha t that can be pulled out in common. And the rest has an e to the I omega t plus e to the minus I omega t, which I can also write as cos plus sine. So this can be equivalently written as y of t equals some c e to the minus I alpha t times, or some e to the minus I alpha t times some c1 cosine omega tilde t plus c2 sine omega tilde t. Okay. Or I can write this as some constant times e to the minus I alpha t times sine of omega t plus some phase delta. So all these forms are equivalent. Okay. So how does this look like? This is quite interesting because there is an oscillating component and there is also an exponentially decaying component. So there is an e to the minus I alpha t. So obviously for very, very large t, the e to the minus alpha t is going to dominate and pull everything down. So that is a given. But there is also an oscillating piece here. So the way this graph is going to look like is as follows. When you pull the bob and let it go, it's going to start oscillating. Okay. It's going to start oscillating, but the amplitude of oscillations is going to get smaller and smaller and finally die down because of the e to the minus I alpha t term. So it's going to go something like this. I mean, this is a blown up version. Okay, so on and so forth. So there'll be an envelope here. The way these amplitudes drop down is accordance with e to the minus alpha t. So this is the e to the minus I alpha t. This is y of t as a function of time. So this is the underdamped case. Underdamped because the oscillations don't go down to zero straight away. They start oscillating, but because of this exponentially decaying term, for large t, the oscillations are going to die down. And this serves as an intermediate between the overdamped and critically damped. So the critically damped is sort of an intermediate between these two. But if the damping coefficient is not too large, but still big enough to cause damage, this is what happens. Okay. So, you have seen other examples of these constant coefficient problems in your LCR circuits and things like that, which we won't repeat here. But there is a nice discussion in your textbook, which I invite you to go through. Okay. So this completes our discussion of linear, homogeneous, ordinary differential equations of order 2 with constant coefficients. And now I would like to switch gears and talk something about the solutions of general homogeneous second order differential equations. But before I do that, are there any questions about any of this? Any questions or any comments? Have you guys seen this in your high school, these constant coefficient problems? Oh, okay. All right. So next we move on to a slightly different topic. And this has to do with existence and uniqueness of solutions. So just like we asked in the case of first order differential equations, under what conditions does a solution exist and under what conditions is a solution unique. We want to ask the exact same questions in the present case of second order differential equations. Okay. So let us first write down what the initial value problem is that we're interested. So the general initial value problem is y double prime plus p of x y prime plus q of x y equal to 0. We have relaxed the constant coefficient part. So we are once again back to p of x and q of x as some functions of x. Okay. But we are still sticking with the homogeneous part. We are not still adding an inhomogeneous term that we will look at in the next lecture. And this becomes an IVP, one initial value problem. Once I specify the values of y and y prime at some value of x. So I will make this into an initial value problem by claiming that y at x0 is some k0 and the derivative of y at x0 is some k1. Okay, so this is, I'll call this equation 1 and this is my initial value problem. So by now you know that there are two linearly independent solutions and the general solution can be written as a linear combination of these two. Okay, and once I talk about an initial value problem, I don't talk about a general solution because I fix the constants, right? So I know that I can write y as some c1 y1 of x plus c2 y2 of x. This is the general solution. But now the initial conditions y at x0 equals k0 and y prime at x0 equals k1 fix c1 and c2 and I get a unique solution. I get a specific particular solution for y. Okay. So the question really is, under what conditions does this solution exist and under what conditions is the solution to this initial value problem unique? So the answer to this is provided by a theorem and I will simply write down this theorem without proof. If p of x and q of x are continuous functions on some open interval I. Okay, and the initial value point x0 is in I. That is important. Then the initial value problem as defined in equation 1 has a unique solution y of x on the interval I. And you will notice that this is much simpler than what we had in the case of first order differential equations. Remember in the case of first order differential equations that the existence was guaranteed by the continuous function p of x and uniqueness was only guaranteed if I write the differential equation as y prime equals f of xy, if df dy was also continuous and bounded. But in this case, the continuity of p of x and q of x basically guarantee uniqueness of the solution. Of course, uniqueness of the solution simply means the solution also exists. We'll talk about the general solution as we go along. So I will state it as such and we will first try to understand what this equation really means. Okay, so this will be the goal of the next half an hour of the lecture. What really is linear independence and what does this mean? So this is stated as a theorem in your book. So I'll follow the same terminology, even though this is not how I learned it, but that's fine. So what is this theorem? The theorem says that let p of x and q of x be continuous on some interval. Interval means some distance in x. So x between say a and b, whatever it is. Then two solutions y1 and y2 on this interval are linearly dependent on I if and only if their Wronskian defined as, I define a new function w, which is a function of y1 and y2, and in turn is a function of x because y1 and y2 are functions of x. The way I define this is y1, y2 prime minus y2, y1 prime is 0 at some x0 on I. Okay, so this is a rather big statement. There is a bunch of statements, but we'll unpack them one by one. Furthermore, if w equals 0 at x equals x0 at one single point in I, then w equal to 0 on I, the entire region. Okay, so all you have to check is if w equals 0 at some point in the interval. Hence, if there is an x1 in I at which w equals 0, then y1, y2 are, so w is not equal to 0 rather, are linearly independent on I. So there's a whole bunch of statements I wrote here, and you can also find these statements in a textbook, but let us try to understand what this means. So thus far, we have defined linear independence of the solution in the following way. So I wrote y of x equals some k1 y1 plus k2 y2. And then I told you that, look, if the solution for this k1 y1 plus k2 y2 equal to 0 is the only trivial solution where k1 equals k2 equals 0, then y1 and y2 are linearly independent. If, on the other hand, I'm able to write down a solution for this for non-trivial k1 and k2, in other words, if this implies that y2 is minus k1 over k2 times y1, then the solutions are linearly dependent on each other, which means that the ratio of y2 over y1 is just a constant. In which case y1 is not really an independent function, because I know if I know y2, I can just multiply it by some constant and get y1. So there is no independent way of getting y1. So this is the way in which we have motivated linear independence, and this is perfectly fine. Now we want to make it a little more precise. So the way I would do it is as follows. So look, I have an equation, and the equation that I want is k1 y1 plus k2 y2 equal to 0. The question is, does a solution for this equation exist? And well, I have two constants. So let me differentiate this expression and get a second equation. k1 y1 prime plus k2 y2 prime should be equal to 0. So this trivially follows from the first equation. Okay. All right. Okay. So now I have a system of, so go back to your linear algebra, you have a system of two equations with two unknowns. The unknowns here are k1 and k2 because you know y1 and y2. And the question is, can I figure out a non-trivial solution for k1 and k2? So if you want, you can write this in matrix notation. So I will write this as y1, y2, y1 prime, y2 prime, acting on k1, k2 equals 0. A 2 by 2 matrix acting on a column vector with entries k1 and k2 is equal to 0. This is my matrix equation. And the question is there a column matrix, a non-zero column matrix, such that this equation is valid? Okay. So can anyone remember their linear algebra and tell me what the answer is? If I want, So if I don't want k1 equals 0 and k2 equals 0, if I want k1 to be non-zero and k2 to be non-zero, what does this mean? This means that I'm asking what is the condition for linear dependence. If k1 and k2 are 0, I know that the solutions are linearly independent. So I'm asking what is the condition for linear dependence. Does anyone, can anyone take a guess? Any guess is fine.
y1 y2 prime minus y2 y1 prime is 0.
So the determinant of this matrix should be 0 or non-zero. For k1 and k2 to be non-zero, you're on the right track.
It should be 0, right?
So the point is, suppose if an inverse of this matrix exists, right? So I can simply multiply by the from the left by the inverse of this matrix. Okay, if the inverse exists, then I multiply by the inverse. So let us call this matrix some capital Y, and this as some column vector K, and this is equal to Y times K equal to 0, right? So if an inverse of Y exists, then Y inverse Y K also has to be equal to 0. And this simply means that K has to be equal to 0. This is a trivial, cheap way of seeing this, right? Which means if the inverse of this matrix exists, then the only solution possible is K1 equals 0, K2 equals 0. But the inverse can only exist if the determinant is non-zero. So if the determinant is non-zero, then the only solution is k1 equals k2 equals 0. If the determinant is 0, then I can have non-zero k1 and k2 for which this equation is valid. So if determinant of y1, y2, y1 prime, y2 prime is not 0, then I should necessarily have k1 equals k2 equals 0 for the above equation to be valid. But what is this determinant of y1, y2, y1 prime, y2 prime? This is exactly what we have defined as the Wronskian here. So this is basically w of y1 comma y2 equals y1, y2 prime minus y2, y1 prime. So there is nothing mysterious about this particular definition. How did it come about suddenly? It simply has to do with the determinant of this particular matrix. And if you guys remember your linear algebra, this is pretty standard. Okay. So if the Wronskian is not 0, then the solutions are linearly independent. Okay, so let us actually do an example. So this is obvious to you. So let us consider the two solutions of this equation, y double prime plus omega square y equals 0. The two solutions are y1, y2 equals cosine omega x and sine omega x, right? So let's put them as a matrix with the upper row populated by y1, y2 and the lower row populated by the derivative of y1 and y2. So, and take the determinant of this matrix. So y1 is cosine omega x, y2 is sine omega x, y1 prime is minus omega sine omega x, and y2 prime is omega cosine omega x, and this obviously is just omega. And this is obviously not equal to 0. Okay. So since the Wronskian of these two solutions is not 0, this necessarily means that cosine and sine are linearly independent functions. So take another simple function. So remember that one of the examples that we worked out was something like reduction of bases, right? So we had one solution y1, and the second solution is x log x or x squared log x. I don't remember, but both of them would work. So let us figure it out, figure out the Wronskian for these two cases also. Put the solutions on top, x and log x. Okay. Sorry, x and x log x. X log x, okay. And the derivative down below. So this derivative of x is 1, and the derivative of x log x is log x plus 1. Okay. So this determinant obviously is x log x plus x minus x log x, which is just x. Okay. And in any open interval that doesn't include x is equal to 0, where the second function isn't defined anyway, this is obviously not equal to 0. Okay, so where we can safely conclude that x and x log x are linearly independent solutions because their Wronskian is non-zero. So these are very easy examples that you can easily work through. So when W Wronskian is not equal to 0, from simple arguments of linear algebra, you can clearly understand that these solutions are linearly independent. So we can also work out the other way around. So if what happens if W equal to 0? If W equal to 0, this implies that y1, y2 prime minus y2, y1 prime equal to 0, right? That's what the Wronskian means. So this simply means that y1, y2 prime equals y2, y1 prime, and I can easily integrate this because it's a separable equation. So I can write this as y1 prime by y1 equals y2 prime by y2. And what is the solution to this equation? If I integrate this, this would simply mean that y1 prime is y1 of x is c times y2 of x, or the other way around. Y2 is some constant times y1. So if the Wronskian is equal to 0, it's also very easy to check that the solutions are indeed linearly dependent on each other because the ratio of these guys is just a constant. So knowing one, I know the other. Okay. But Wronskian is also slightly more powerful. So let us now go back to this theorem and take a look at it. So we have shown the first part, right? So if W is 0, then it is certainly linearly dependent. Conversely, if W is non-zero, as we have showed in these examples, they are linearly dependent. Sorry, if W is non-zero, they're linearly independent. Okay, but that is not all it says. So if W is equal to 0 at some x is equal to x0, then W is equal to 0 on the entire interval. So this is actually a very powerful statement. So it tells you that if you evaluate the Wronskian at some particular point and you find it to be 0, then you're guaranteed that for the solutions that you have, not any arbitrary functions, for the two solutions that you have, W has to be 0 everywhere on that interval. Okay. Conversely, I can take the converse of this and say that, look, if W is 0 at one point, it is 0 at all points in the interval. Which means if I can find even one point where the W is non-zero, then I can be guaranteed that the Wronskian is non-zero at all points. And if the Wronskian is non-zero at all points, then the two solutions are linearly independent. Okay, if this looks confusing, we will go in small steps. So the first statement that we are making with this theorem is that suppose if W equals 0 at some point x is equal to x0. Then we can argue that W is 0 on all points. And so the two solutions that you have at hand are linearly dependent on each other. Conversely, if there is at least one point in the interval where the Wronskian is non-zero, then the Wronskian has to be non-zero at all points, which means that the two solutions are linearly independent. So we'll try to understand what this means in a little more detail. First of all, notice that I cannot make an argument like this for the function. So let us take cosine and sine, right? So I cannot claim that suppose, hey, look, I take cosine and sine, okay? And then I have some interval, x is equal to some 0 to 2 pi. And then I cannot make the argument, look, but at x is equal to pi by 4, cosine and sine are the same. So they are linearly dependent. So this is not valid for functions, you see, the y1 and y2 itself. This statement is only valid for Wronskians. It doesn't make any sense. Cosine and sine, as you have figured out, or as you already know, are linearly independent functions. So I cannot take some x is equal to x0 and argue that since cosine happens to be the same as sine at this particular point, the two solutions are linearly dependent. That's not how it goes. But I can make a similar statement about the Wronskian. I can take some particular point x is equal to x0 in the interval that I'm looking at. And If the Wronskian is 0 or non-zero in that point, then I can safely say that the Wronskian would be 0 or non-zero at all points in the interval that I am looking at. So let us actually, since this is slightly important, I will explain this a little more carefully. So here's what I mean. So let W of y1, y2 be non-zero at some point x0. Okay, so what I'm basically saying is y1, I'm computing y1 at x0, y2 at x0, and computing the Wronskian of the solutions at that particular point x0, and this is not equal to 0. And I don't know about other points. I only know about that particular point. Okay, so let me form a system of equations just like I formed over here, except that this time I will form the system of equations at x is equal to x0. So then k1 y1 at x0 plus k2 y2 at x0 equal to 0, k1 y1 prime at x0 plus k2 y2 prime at x0 equals 0. This is the system of equations just like we had before, except that it is evaluated at the point x is equal to x0 where my Wronskian is guaranteed to be non-zero. Now multiply this equation by I don't know, y2 prime, and multiply this equation by y2 and subtract. What happens? If I multiply the first equation by y2 prime, I get a term like k2 y2 prime y2. And if I multiply the second equation by y2, I get a term like k2 y2 y2 prime. And if I subtract, these two guys go away. So if I subtract, I get k1 y1 y2 prime minus y2 y1 prime equals 0. And this simply means that k1 Wronskian at w at x is equal to 0 equals 0. Okay. Now, what does this mean? So this is a lousy notation, w at x is equal to 0. I simply mean that w, which is a function of y1 and y2, and both evaluated at the point x is equal to x0. Since it is laborious to write, I'm simply using this shorthand notation. Similarly, you can do a slightly different manipulation and multiply the first equation by y1 prime and multiply the second equation by y1 and subtract. And you can also get k2 w of x0 equal to 0. Now, if w at x0 is equal to 0, then this equation has a trivial solution, right? So I can simply divide, if w is equal to 0, then I will simply say that oh, w equal to 0, so that's why these two equations are 0. But since w is not equal to 0, these two equations can be satisfied in principle by some non-zero k1 and k2. Okay, this is the exact statement that we had made before. Since I'm guaranteed that the Wronskian at that point x0 is not equal to 0, I can have non-zero k1, k2 that can satisfy these two, this system of linear equations. So I can have non-zero k1, k2 that satisfy, let's call this system A, that satisfy A. Okay, is the argument clear? Since W is non-zero, are there any questions or comments? So give me just a second. Sorry, no. Let me do it the other way around. I'll assume that W is actually 0. So this is slightly easier to do than the other case. So let me assume that W is actually 0. If W is 0, then I can trivially satisfy the system A, right? With non-zero K1, K2 as well. If W, of course, is non-zero, then I can only have K1 equals K2 equals 0. That is the original statement of linear independence, but that is not what I want. So I slightly misspoke here. I want to have W equal to 0 at some point X is equal to X0. So I want to investigate the consequences of this by only assuming that the Wronskian is 0 at one point. I don't know about the other points. Then at least from this particular set of equations, it looks as if I can have non-zero K1 and K2. Okay. Then with this non-zero K1 and K2, whatever non-zero K1 and K2 it is that satisfies this set of equations, I can form a general solution that looks like K1 Y1 of X plus K2 Y2 of X. Does this make sense? Please stop me if there is any question. Since my Wronskian is non-zero at a particular point x0, I can have non-zero K1 and K2 that satisfies the system of equations A. With this set K1 and K2, I form a general solution which I write as K1 Y1 plus K2 Y2. Okay, since K1 and K2 are constants, it doesn't matter if they were only non-zero at the point x is equal to x0. Since they're constants, they have to be constant everywhere. So I'm guessing that I can have non-zero K1 and K2 for this particular problem. Okay, now what happens if I do this? Now, how can I write the solution like this? Well, I'm always guaranteed, because I'm dealing with a homogeneous second order linear differential equation. If I have two solutions, I can always add a linear combination. The linear combination is a solution. So what is the problem that I'm solving? The problem that I'm solving is a general second order homogeneous linear differential equation with the initial value condition y at x0 equal to 0. Why should it be 0? Because k1 y1 at x0 plus k2 y2 at x0 is equal to 0 from the first of these equations. So y at x0 has to be equal to 0, and y prime of x0 also has to be 0 because from this equation. So I am solving a differential equation with this particular initial values, initial value conditions. Okay. But theorem 1 says that, look, as long as you have continuous p of x and q of x, if you have a solution, that is a unique solution. So the question is this a unique solution? I have some solution which is given by k1 y1 plus k2 y2 with non-zero k1 and k2 guaranteed by the Wronskian being equal to 0 at some particular point x is equal to x0. But is there any other solution that also has the exact same property, that y at the point x0 is 0 and y prime at the point x0 is 0? The answer is yes. There is a solution for the same initial value problem, and that is the solution y star of x equal to 0. Again, you can argue that this is a trivial case, but remember that this is only true for homogeneous differential equations. If I add an inhomogeneous term, I can never make this statement. But for this case, this is definitely a solution. It's certainly a valid solution because it certainly satisfies the property that at the point x is equal to x0, y is 0, and trivially y prime is also 0. So since theorem 1 guarantees uniqueness, it guarantees that this function y and this function y star are really the same. So uniqueness means that these are not two different solutions. You have simply written 0 in a slightly non-trivial fashion. That is what the theorem 1 guarantees you, which means k1 y1 plus k2 y2 k1 y1 of x plus k2 y2 of x is actually equal to 0. Okay. And since k1 and k2 are non-zero, this simply means that y1 and y2 are linearly dependent. Okay. So if you don't follow the exact argument, at least appreciate the power of the statement. We started with the assumption that the Wronskian was non-zero at some particular point x is equal to x0. We did not know about any of the other points and what the Wronskian was at any other point. Right? Somebody came and told us that, oh, look, you have a linear second order homogeneous differential equation where p of x and q of x are continuous functions. And I have the solutions y1 and y2, and it turns out that at the point x is equal to 5, the Wronskian is 0. Now, what can I say about the solutions? Then you can claim that, look, I can evaluate this system of equations at the point x is equal to 5. And then I can claim that since the Wronskian is 0, I can have non-zero k1 and k2. And using this information, I can construct a general solution that looks like k1 y1 plus k2 y2, guaranteed by the superposition principle. Okay. And then I investigate what is the problem that I'm solving. I'm solving the initial value problem, y at 5 equal to 0 and y prime at 5 equal to 0. And then I will argue that, look, there is a solution that also has the exact same conditions, and that is the solution y equal to 0. And since you told me that my functions p of x and q of x are continuous, theorem 1 guarantees that the solution has to be unique, which means all I am doing in the first step is writing 0, because these two solutions are exactly the same. There is only one unique solution. But once I write down k1 y1 plus k2 y2 equals 0, where this is at any point x, remember, all I'm saying is that y1 and y2 are linearly dependent because I seem to have non-zero k1 and k2. So what does this mean? This means that the knowledge of the Wronskian being equal to 0 at one point x is equal to 5 guarantees that y1 and y2 are linearly dependent on each other in the entire interval. Okay, so this is the power truly of Wronskians, that this is not true for the functions. Again, as I told you, you cannot just take sine x and cosine x and say that, oh, look, at the point x is equal to pi by 4, the numerical values of these two guys are the same, so they're linearly dependent. It doesn't work that way. But it does work that way for Wronskians. You take the Wronskian of these two guys, and if you're able to find a point at which the Wronskian is 0, then you can, and if this point is in the interval that you're looking at, then you're guaranteed that the two solutions that you have are not linearly independent. They are actually simple multiples of one another. Okay, so we will stop here today, and then we will continue our discussion of Wronskians and general solutions, and then we will move on to inhomogeneous differential equations also in the next lecture. Okay, so before we close, are there any questions or comments?